Point a telescope at any galaxy in the sky tonight, in any direction you like, and it is running away from you. Point it at the exact opposite side of the sky, at a galaxy in the completely opposite direction, and that one is running away from you too. Keep turning. Every galaxy, in every direction all at once, fleeing the same single point in space. That point is you. Taken at face value, that can only mean one thing, and it's an impossible thing, that out of every location in an unimaginably vast universe, you happen to be standing at the exact centre of it. Not metaphorically, mathematically, you're not the centre, nobody is. And the reason that's true, without breaking a single law of physics, without Earth secretly being special, without the universe needing a centre at all, is one of the strangest chases in the history of science. It runs through a man who spent a decade photographing smudges of light nobody understood. A deaf woman paid 30 cents an hour who accidentally handed astronomers a cosmic tape measure. Einstein calling his own equations abominable. And two engineers who thought their antenna was contaminated with pigeon droppings and had actually found the afterglow of the birth of everything. By the end of this, you'll understand something that sounds simple and isn't. Why every point in the universe looks like the middle of it, and why the honest current answer to what lies beyond it all is one science still hasn't finished chasing down. Go outside tonight, away from any city, and look up. If the sky's clear, it will do something remarkably convincing. It will hold still. The stars keep their positions relative to one another, night after night, year after year. Orion's belt tonight is Orion's belt as it was sketched onto a Babylonian clay tablet 3,000 years ago. The Big Dipper has not spilled a drop in all of recorded human history. To the naked eye, watched for as long as an entire human life lasts, the universe looks like the one truly fixed thing in existence. An unmoving backdrop against which everything else, the weather, the tides, the seasons, our own small and hurried lives, plays itself out. This isn't a new observation. It's arguably the oldest assumption in the history of astronomy. Aristotle believed the heavens were made of a fundamentally different, unchanging substance than the corruptible, ever-shifting world down here on Earth. The stars didn't age, didn't decay, didn't go anywhere, because they belonged to a category of existence that simply didn't do those things. Centuries later, Isaac Newton, building the physics that would define science for the next 200 years, quietly assumed an infinite static universe as the backdrop for his equations. Space as a fixed stage, existing forever, changing not at all on the grandest scale, with stars merely sitting in it the way furniture sits in a room. Newton worried, in his letters, about why such a universe wouldn't simply collapse in on itself under its own gravity. And even that worry didn't lead him to imagine the universe might instead be moving. It was, to nearly everyone who had ever looked up, simply obvious. The sky is the fixed thing, and everything else moves against it. That impression is one of the most convincing illusions the universe has ever handed us. And it is wrong, in a way so deep and so slow to reveal itself that it took the better part of a century, several careers, and the collapse of a few extremely confident theories to actually understand. Here is where we start pulling on the thread. So let's actually earn that opening claim, because everything is running away from you isn't something to just take on faith. It comes from something you can, in principle, verify yourself, the light itself. When something emitting light moves away from an observer, the light gets stretched, its wavelength lengthens, shifting toward the red end of the visible spectrum. It's the same basic principle as an ambulance siren dropping in pitch as it speeds away from you. The sound waves are being stretched out behind it, and your ear hears that stretching as a lower note. Light does something equivalent. Astronomers call it redshift, and by the early 20th century they had built instruments precise enough to measure it reliably. That part on its own is unremarkable. Things moving away and showing redshift is not strange. What's strange is what happens the moment you measure thousands of them and start looking for a pattern, which is exactly what one very patient man was about to do starting in a cold observatory dome in Arizona. Picture this happening on a highway. Every single car, in every lane, in every direction, driving away from the exact spot where you're standing. No car approaching. No car staying level with you. Every one of them, without exception, getting farther away. You would draw one obvious, almost unavoidable conclusion. You are the origin point. Whatever this is, it's centered on you. That's a very strange conclusion for a species living on a modest rocky planet, orbiting an unremarkable star, tucked into an unremarkable arm of an unremarkable galaxy. Nothing about our address in the universe has ever suggested we deserve to be the center of it. And yet, taken at face value, the data point's exactly there. That's the second problem hiding inside the first one. The pattern implies a center, but every instinct astronomy has ever developed says there shouldn't be one. And here's a third layer. Quieter, but in some ways stranger than the first two. Sort those fleeing galaxies by distance, the close ones from the almost incomprehensibly far ones. And a second pattern shows up nested inside the first. The farther away a galaxy is, the faster it appears to be receding. Not loosely, almost exactly proportionally, double the distance, and you roughly double the speed. Push that relationship out to galaxies whose light has been travelling toward us for billions of years, and the implied recession speed exceeds the speed of light itself. That should be flatly impossible. Nothing, in over a century of relentless testing, has ever been caught moving through space faster than light. And yet here is an entire class of objects that appears to be doing exactly that, and doing it more dramatically the farther out you look, as if the rule breaks down worse and worse with distance, on purpose. 3 separate observations, each perfectly fine in isolation, stacking into something that shouldn't cohere at all. Everything is fleeing specifically from us, which implies a center that shouldn't exist. The flight gets faster with distance, in a relationship too clean to be an accident. And past some threshold, the flight speed breaks a law of physics that has never once been broken anywhere else, in any experiment ever. Here's the twist this whole documentary is going to slowly walk you toward. This was never really a mystery about galaxies. It's a mystery about the thing they're sitting in. Because the answer, the one that took decades of careful, uncomfortable, repeatedly doubted science to actually arrive at, is that the galaxies are not the ones doing most of the moving. Space itself is changing shape underneath them. And once you let yourself take that seriously, a much bigger, much stranger question opens up behind it. If space is expanding, where is the new space coming from? And is there anything for it to be expanding into? That's the real question this whole film is chasing. Not, why are galaxies moving? But, what does it actually mean for space itself to grow? And what, if anything, lies past the growing edge of it? We're going to take this slowly, exactly the way it was actually pieced together in real life. One uncomfortable data point at a time, across a century of brilliant people whose gut instincts were again and again instructively wrong. If you've ever wondered how something this big gets figured out, not in a single flash of genius, but stitched together across generations of people who mostly didn't know they were building toward the same answer, this is that story. Before any of this could be pieced together, somebody had to sit and look, patiently, without expecting anything in particular to be there. In the early 1910s at Lowell Observatory, perched on a hill outside Flagstaff, Arizona, an astronomer named Vesto Slipher took on a job that sounds frankly a little tedious. He spent years photographing the spectra of faint, fuzzy patches of light called spiral nebulae. Nobody was entirely sure what these things even were. Some astronomers suspected they were nearby clouds of gas, still swirling inside our own galaxy, in the slow process of collapsing into new stars and planets. The far bolder idea that these smudges might be entire separate galaxies, each containing hundreds of billions of stars, sitting at distances so vast they defied ordinary comprehension, was not yet an accepted fact. It was a fringe guess. Spectroscopy, the technique of splitting a source's light apart into its component wavelengths, was mature enough by this point to reveal something extremely useful. Certain elements, like hydrogen and calcium, absorb and emit light at very specific, well-known wavelengths, producing a distinct pattern of lines. Think of it as a fingerprint baked directly into the light itself, and when the object producing that fingerprint is moving toward or away from you, the entire fingerprint shifts, toward blue if it's approaching, toward red if it's receding, by an amount directly proportional to how fast it's moving. Slipher measured spiral nebula after spiral nebula with an almost stubborn patience, using exposure times that sometimes stretched across many hours over multiple consecutive nights, because these objects were so faint that the instruments of his era could barely register them at all. Picture that for a second. A man in a cold observatory dome night after night, painstakingly guiding a telescope by hand to keep a barely visible smudge of light centered on a photographic plate for hours, waiting for enough photons to trickle in to form a usable image. This was not glamorous work. There was no reason, going in, to think it would rewrite anyone's picture of the cosmos. What he found, published in stages between 1912 and the early 1920s, was quietly startling. The overwhelming majority of these nebulae showed redshifts. They appeared to be receding, and some of them at speeds several times greater than any ordinary star's motion within our own galaxy. At the time, there was no framework demanding this result, no theory predicting it, nothing telling Slipher he should expect it. The prevailing assumption, so deeply embedded that it rarely needed to be stated out loud, was that the universe, whatever its true extent turned out to be, was essentially static on the larger scales. Stars moved locally. Galaxies, if that's even what these smudges were, might drift a little, the way any loose collection of objects drifts under mutual gravity. But the universe as a whole was treated as a fixed stage on which more local events simply played themselves out. Even Einstein didn't escape this assumption. When he applied his brand new theory of general relativity to the universe as a whole, in 1917, he found that his own equations flatly refused to describe a static, unchanging cosmos. They wanted, mathematically, to describe a universe that was either expanding or contracting. There was no version of the math that just sat still. Rather than accept that implication, Einstein inserted an extra term into his own equations, a cosmological constant, engineered for one specific purpose: to hold the universe motionless, precisely cancelling out gravity's natural tendency to make everything either collapse inward or fly apart. He needed the universe to be at rest, so he built a patch directly into the mathematics to force it to be. It's worth pausing on that, because it tells you exactly how strong this assumption really was. One of the most rigorous, most mathematically fearless physicists in history looked at his own theory, watched it predict motion, and chose to override that prediction rather than seriously entertain the possibility that the cosmos itself might not be sitting still. Slipher's spectra sat somewhat outside this entire argument for years, treated mostly as an interesting curiosity about one particular class of faint, poorly understood objects. Evidence, at most, that these nebulae had some unusual local dynamics of their own. Not evidence about the structure of the universe as a whole. Nobody yet had the second piece of information needed to reinterpret what he'd found, how far away these things actually were. This is the shape science often takes, and it's worth sitting with before we move forward, because it will happen again later in this story. An anomaly can exist in plain sight, faithfully recorded, correctly measured down to the decimal, and still mean almost nothing, because meaning requires context, and the context hasn't arrived yet. Slipher had discovered that the sky was moving. He had not yet discovered why that mattered. He would spend the rest of his working life mostly uncredited for what came next, because the next piece belonged to somebody else, at the same observatory, working with a far bigger telescope. Before we follow that next piece to Edwin Hubble, there's a person who has to come first, because without her, none of what Hubble did would have been possible, and for most of the 20th century, her name was barely mentioned in the story at all. Measuring the distance to something you cannot travel to, cannot mark with a physical ruler, and cannot triangulate the ordinary way is one of the oldest and hardest problems in the whole history of astronomy. The breakthrough came from an unexpected place. A research group at Harvard College Observatory known, at the time somewhat coldly, as computers, a team made up almost entirely of women, hired specifically because the observatory could pay them a fraction of what it would have paid a man, to do the extremely detailed, extremely repetitive work of cataloguing and measuring thousands of photographic plates. One of them was Henrietta Swan Leavitt. She was profoundly deaf, likely as a result of an illness, and she worked for years at Harvard for a wage that, by some later estimates, worked out to about 30 cents an hour, cataloguing the brightness of stars on photographic plates with a handheld magnifying glass, plate after plate, for a director who would later take primary credit in public settings for conclusions built almost entirely on her work. In 1908, and then in more detail in 1912, studying a class of pulsating stars called Cepheid variables inside a satellite galaxy called the Small Magellanic Cloud, Leavitt noticed something enormously, almost absurdly useful. Cepheids brighten and dim on a very regular cycle. Some pulse quickly, over just a few days, others slowly over many weeks, and the length of that pulse cycle is tightly, precisely linked to the star's true, intrinsic brightness. A Cepheid that pulses slowly is, reliably, a genuinely more luminous star than one that pulses quickly, because all the Cepheids she was studying happened to be roughly the same distance from Earth, clustered together inside the same small, distant galaxy. She could compare their pulse periods directly against their apparent brightness and extract that relationship with real clarity, without distance getting in the way and muddying the comparison. This is worth sitting with for a moment because of what it actually hands you. If you know a star's true, intrinsic brightness, its wattage, essentially, and you separately measure how dim it looks from here, the gap between those two numbers tells you, with real precision, how far away it is. Light fades from a source in a very exact, calculable way with distance. So Leavitt had, without fully realizing the scale of what she had handed the field, turned Cepheid variables into what astronomers now call standard candles, a kind of cosmic tape measure that worked at distances no other technique of the era could reach. In the mid-1920s, using the 100-inch telescope at Mount Wilson in California, at the time the most powerful instrument on the planet, Edwin Hubble went looking for exactly this kind of star inside several of the spiral nebula Slipher had spent a decade measuring, including the Andromeda Nebula. He found one. Using Leavitt's relationship, he calculated its distance, roughly 1 million light-years. That number on its own ended a long, heated argument in astronomy almost overnight. Andromeda wasn't a nearby cloud of gas drifting inside the Milky Way. It was an entire separate galaxy, sitting so far outside the known boundaries of our own that the universe had, in a single measurement, become dramatically, almost dizzyingly larger than most working astronomers had allowed themselves to seriously imagine. That discovery alone would have made Hubble's career. But he went one step further, and this is the step that actually starts this whole story moving. Hubble combined his new distance measurements with Slipher's existing redshift data, plotting one against the other for every galaxy he had both figures for. The result, published in 1929, is now one of the most famous graphs in the history of science. Deceptively simple looking, a scatter of points that any of us could plot on a piece of graph paper, and yet it quietly rewrote what the universe was. The pattern was almost too clean to believe at first. Galaxies twice as far away were receding at roughly twice the speed. galaxies 3 times farther were receding at roughly 3 times the speed. The relationship was close to a straight line, recession speed proportional to distance, and it held galaxy after galaxy, with a consistency far too tight to explain away as coincidence or sloppy measurement. This relationship is now called Hubble's law, and the number connecting distance and recession speed is called the Hubble constant. Still, to this day, one of the most fought over figures in modern physics, for reasons we'll get to later, because even now, a full century on, nobody quite agrees on its exact value. But stop and notice what this graph actually implies if you take it completely at face value and go no further. Every galaxy is receding from us, and the farther away it is, the faster it's receding. Now imagine an alien astronomer standing on a planet inside one of those distant galaxies, running the identical analysis with their own instruments. What would they conclude? They would conclude exactly what we did, that everything is receding from them, faster the farther away it gets. They would plot the identical graph. They would arrive at the identical uncomfortable implication that they too appear to sit at the centre of some great cosmic exodus. Both of those things cannot be true at once, at least not in the naive way it first appears. Either the universe genuinely has a centre and we happen to occupy it, a staggeringly improbable claim for any single observer anywhere to make about themselves, or something else entirely is going on. Something in which every observer, no matter where they stand in the cosmos, sees the identical pattern, with none of them being special. That something else is the door this part of the story is standing directly in front of. And Hubble's own data, brilliant as it was, didn't walk through that door by itself. Hubble was a careful, cautious interpreter. He documented the relationship with real precision, but for years resisted committing to the boldest reading of it, that space itself was physically expanding. That leap had already been made mathematically 2 years before Hubble even published, by someone whose work had been sitting almost entirely ignored, a Belgian Catholic priest and physicist named Georges Lemaitre. In 1927, 2 full years before Hubble's paper, Lemaitre published a solution to Einstein's own general relativity equations describing a universe that expands over time. He went further than that, using early redshift data, including some of Slipher's original measurements, to estimate a value for the exact same expansion rate Hubble would later calculate independently from the other side of the Atlantic, apparently unaware of Lemaitre's work. Lemaitre's paper appeared in a relatively obscure Belgian scientific journal, written in French, and it went almost completely unnoticed by the wider physics community for 2 full years. This is worth sitting with, not as a footnote, but as a genuinely strange fact about how discovery actually works. The correct answer to one of the biggest open questions in physics existed, in print, sitting on a library shelf for 2 years, essentially unread by the people who most needed it. When Lemaitre finally got the chance to discuss the idea directly with Einstein at a conference in 1927, the reaction was not encouragement. Einstein reportedly told him his physics was correct, but that his cosmology was abominable. That single word tells you almost everything about how unthinkable an expanding universe still seemed, even to the one person on Earth best positioned to recognize it in his own equations. Einstein, remember, had already gone out of his way to modify those very equations specifically to avoid this exact conclusion. It's worth sitting with that moment a little longer, because it's an unusually clean example of just how badly a strong prior assumption can distort even a genuinely brilliant mind. Einstein wasn't resisting Lemaitre because the mathematics was flawed. He resisted because a static, eternal universe felt, on some deep intuitive level, like the only sane universe there could be. A cosmos that had simply always existed, more or less in its current form, without a beginning and without dramatic change. An expanding universe carried an unavoidable implication. Run the expansion backward in time, and everything had once been smaller, denser, hotter, compressed further and further back towards some kind of origin state. That implication deeply unsettled a great many physicists in the 1920s, for reasons that were, frankly, more philosophical and even theological than mathematical. It sounded uncomfortably close to a creation event, and many scientists of that era were actively wary of physics that seemed to be smuggling theology in through the back door of an equation. By 1931, with Hubble's independent observations now public and increasingly impossible to wave away, Einstein changed his position. He is widely quoted in later years as calling the cosmological constant, the exact term he had inserted specifically to keep the universe motionless, his biggest blunder. Historians have debated whether he used those precise words, but the substance of the story isn't in serious dispute. Einstein publicly abandoned the term, and general relativity, left unmodified, was free to describe the universe it had wanted to describe all along, one that expands. This matters for more than just historical colour, and it's a pattern worth keeping in mind for the rest of this story. Again and again, the mathematics turned out willing to describe a far stranger universe than the physicists studying it actually wanted to believe in. Static felt safe, expanding felt radical, and the data, patiently, stubbornly, kept siding with radical. Once an expanding universe was accepted, it didn't resolve the discomfort we started with. It relocated it. If space itself is expanding, and every galaxy is receding from every other galaxy at a rate proportional to distance, we land right back on the uncomfortable question from the very beginning of this story, now sharpened to a fine point. Does this mean the universe has a literal physical centre, an actual origin point everything is fleeing from? And if it does, why does it look, from right here on Earth, exactly as though we happen to be sitting on top of it? This is where something called the cosmological principle enters the story, not as a new piece of data, but as an assumption so foundational to modern cosmology that it's worth stating plainly before we go any further. On the largest possible scales, the universe is assumed to look roughly the same in every direction you look, and from every location you could stand. No special points, no privileged vantage point anywhere. Earth isn't favoured, isn't. The Milky Way isn't favoured. No galaxy anywhere in the cosmos gets to claim the actual geometric centre of everything. Part of this is philosophical inheritance, a direct scientific descendant of the Copernican shift, away from treating Earth as cosmically special, the same instinct that moved us from the Sun orbits us to we orbit the Sun 4 centuries earlier. But it's also increasingly an empirically tested claim, not just a comforting assumption. Large-scale surveys mapping the positions of hundreds of thousands of galaxies show a universe that, averaged out over sufficiently large volumes, really does look statistically uniform in every direction we've measured. Clumpy up close, sure, galaxies cluster together, and those clusters cluster into even larger superclusters, forming the largest structures we know of, but smoothed out at the truly largest scales into something remarkably close to uniform. So, if the cosmological principle holds, the naive reading of Hubble's law, we're the centre, everything is fleeing specifically from us, simply cannot be the right interpretation. So, what is? The resolution comes from taking the actual mathematics of an expanding universe seriously, rather than picturing it the way you'd instinctively picture an explosion in a room, shrapnel flying outward from one central detonation point into space that was already sitting there waiting for it. That picture, as intuitive as it feels, is exactly the wrong model. Untangling why it's wrong is the real heart of this entire mystery, so let's slow all the way down here. In an explosion, objects move through a fixed pre-existing space, away from a specific point where the detonation happened. There's a real, physical centre, the exact spot the explosion occurred, and pieces of shrapnel are getting farther from that centre, and, as a side effect, farther from each other too. Cosmic expansion is not that. In cosmic expansion, it is space itself, the very fabric that defines distance between things, that is growing. Galaxies are not, for the most part, flying through static, pre-existing space away from some point of origin. They're approximately sitting still relative to the space immediately around them, and it's the space between any two sufficiently distant galaxies that is simply continuously stretching everywhere at once, without any of it needing to have originated from one specific spot. That single distinction dissolves the "are we the centre" problem entirely. In a model where space itself expands uniformly everywhere, there is no location that qualifies as a centre, because every point sees every other point receding from it in every direction, faster with distance. Not because that point is special, but because that is simply what uniform expansion looks like from the inside, from any vantage point at all, without exception. This is genuinely difficult to hold in your head, because every physical intuition we've built up from living inside 3 dimensions is an intuition about objects moving through space, not about space itself changing size. We've never had a reason, in ordinary daily life, to imagine distance as a quantity capable of growing on its own, independent of anything actually moving through it. So physicists reached for lower dimensional analogies. They're imperfect, but 2 of them, taken together, do a genuinely remarkable job of making this click. Picture a loaf of raisin bread dough before it goes into the oven, with raisins scattered evenly all the way through it. As the dough bakes and rises, it expands, and every point inside it gets farther from every other point. Pick any single raisin and ask from its point of view what's happening to all the other raisins around it. Every single one of them appears to be moving away from it. Raisins that started out twice as far away end up moving apart twice as fast. Not because they're moving faster in any active sense, but simply because there is twice as much dough between them, and all of that dough is expanding at the same proportional rate, everywhere, uniformly. No single raisin is at the centre of the loaf's expansion, in the sense of being the source of it. Every raisin sees the identical pattern, universal recession, worsening with distance, and every single one could quite reasonably conclude it's the one sitting still while everything else runs away. They'd all be equally right and equally wrong, because the real action was never happening to the raisins at all. It was happening to the dough between them. This is genuinely close to the actual physics. Galaxies are, loosely, the raisins, mostly just sitting still relative to the local space immediately around them, while it's the dough, space itself, that is doing the expanding, carrying the galaxies apart as a side effect of its own growth. The second analogy fixes the biggest flaw in the first one. A loaf of bread has an edge, a crust, a boundary, and the universe, as far as we've ever been able to tell, might not. So picture instead the surface of a balloon, with small dots drawn across it as it's slowly inflated. Stand as one of those dots. As the balloon fills with air, every other dot on its surface moves farther away from you. Again, with the farther dots receding proportionally faster. The advantage here is that the surface of the balloon is a genuinely 2-dimensional space, with no edge and no centre within itself. A dot on that surface, if it could only perceive the 2-dimensional surface and nothing else, would find no boundary to ever walk toward, and no special central point marking the middle of its universe, no matter how far it travelled in any direction. Every direction looks equivalent. Every point looks, from its own local perspective, exactly like the middle. Where the balloon's actual 3-dimensional centre sits, the empty pocket of air inside the rubber, is not part of the 2-dimensional surface universe at all. It's not a place the dots could ever travel to or even point toward, because it simply isn't part of their space. It's one entire dimension removed from anything they could ever experience or measure. Some cosmologists lean on exactly this feature to illustrate a genuinely strange, but mathematically coherent idea. It may be meaningless, not just difficult, but meaningless, to ask where the centre of our own universe's expansion sits in any dimension we have access to. Because if such a centre exists at all, it would have to sit entirely outside the 3 spatial dimensions we can move through, observe, or ever point a telescope toward. Here's a third way to picture it, one that helps with a slightly different piece of the puzzle. Imagine an infinite flat rubber sheet, stretched out with a grid drawn across it in permanent marker, and imagine that sheet being stretched uniformly in every direction at once, not from any edge, because it has no edge, just uniformly, everywhere, all at the same time. Every square of the grid gets bigger, every intersection point moves farther from every other intersection point, and because the sheet is infinite, there is no edge for the stretching to be moving toward, and no centre for it to be moving away from. It's simply everywhere, becoming more of itself. If our universe turns out to be spatially infinite, a real possibility current data doesn't rule out, which we'll get to later, this is arguably the single most physically honest of the three pictures, even though it's the hardest one to actually visualize, precisely because infinite things resist being pictured at all. All three analogies, importantly, are imperfect, and it's worth being honest about exactly where each one breaks, because false confidence in an analogy is its own quiet kind of misunderstanding. A raisin loaf genuinely does have a centre and an edge in three-dimensional space, even if the raisins themselves could never easily identify either one from the inside. A balloon surface really is finite, and really does curve back on itself, which may or may not be true of our actual universe. Current measurements suggest the observable universe's geometry is extremely close to spatially flat, which would be consistent with an infinite universe, though the data can't rule out an extremely large finite one that would simply appear flat within the volume we're capable of measuring. And the infinite rubber sheet, useful as it is for the no edge, no centre idea, can't easily capture the balloon's more subtle point about a centre existing one dimension removed. No single analogy should be pushed past the one specific feature it's built to illustrate, but the core lesson all three deliver, together, survives every one of those caveats, and it's the resolution to the tension we open this whole story with. The universe having no observable centre is not a paradox requiring some special explanation for why Earth happens to sit there. It's the expected, completely ordinary consequence of uniform expansion, viewed from literally any point inside it. Every civilization's astronomers, wherever in the cosmos they happen to be, looking at their own version of Hubble's law, would reach the same conclusion we did, and every single one of them would be equally correct. Not because they're each secretly the centre, but because centre, in the naive explosion model sense, may simply not be a concept that applies to this particular kind of expansion at all. That resolves the very first anomaly we opened with, but resolving it immediately opens a harder one right behind it, because if it's genuinely space itself doing the stretching, and not galaxies actively moving through static space, then the redshift we're measuring from those galaxies can't simply be an ordinary Doppler shift, the kind produced by objects physically moving through space toward or away from an observer. It has to be something else entirely, and once you take that something else seriously, it explains the third anomaly from the very start of this story, the impossible faster-than-light recession of the most distant galaxies, in a way that, remarkably, doesn't break relativity at all. An ordinary Doppler shift, the kind used to clock a car's speed with radar or measure a star's motion through our own galaxy, works because the emitting object is physically moving through space relative to the observer, compressing or stretching the sound or light waves it's producing as it goes. The object is the one doing the moving. Space is just the passive stage it happens to be moving across. Cosmological redshift is a genuinely different mechanism, even though the visible effect, light shifted toward longer, redder wavelengths, looks superficially identical, and for decades was casually described using Doppler language mostly because that vocabulary was already familiar and close enough for everyday use. Here's the more precise picture, and it's worth slowing down for. Imagine a photon of light leaving a distant galaxy, setting out on a journey toward Earth that will take billions of years to complete. That photon has a specific wavelength the instant it departs. As it crosses the intervening distance, that space itself is expanding, stretching, continuously, the entire time the photon is in transit. Because the photon's wavelength is, in a very real physical sense, stretched right along with the space it's travelling through. exactly like a wave drawn on the surface of that inflating balloon would stretch as the balloon itself grows. The photon arrives at Earth with a longer wavelength than it left with, redshifted. Not necessarily because the source galaxy was moving away from us fast at the exact instant it emitted the light, but because the space between then and now, between there and here, has been quietly growing the entire time that light was in transit. This distinction isn't academic hair-splitting. It fundamentally changes what a redshift number is actually telling you. A cosmological redshift encodes how much the universe has expanded across a photon's entire multi-billion-year journey, not simply how fast its source happened to be moving at one single instant. A galaxy with an enormous redshift isn't necessarily moving away fast in any simple local sense. It's telling you that an enormous amount of cosmic expansion has occurred in the time it took that particular light to reach us, and light from the most distant galaxies we can observe left them when the universe was a small fraction of its current size, which means the space between that ancient light and us has done a truly staggering amount of stretching in the meantime. And this distinction is exactly what resolves the third anomaly, the one that seemed, on its face, to break relativity outright. Special relativity's famous speed limit, nothing can move through space faster than light, is a constraint on motion through space. It says absolutely nothing about how fast the space between 2 points is allowed to grow. There is no clause anywhere in general relativity forbidding the distance between 2 points from increasing at an arbitrarily large rate, because that growth was never the motion of any object through space. It's a change in the underlying geometry of space itself, the very fabric the speed limit applies to, not a violation committed by anything actually travelling across that fabric. So when astronomers calculate that a sufficiently distant galaxy's implied recession speed, extrapolated from Hubble's law out to enormous distances, exceeds the speed of light, they are not describing that galaxy physically hurtling through space faster than light, which genuinely would be forbidden. They're describing the rate at which the accumulated space between us and it is currently growing, summed up across billions of light years of intervening cosmos, where each individual local stretch, taken on its own, is entirely unremarkable and stays comfortably within relativity's rules. It's only the sum across an almost unimaginable span of space that produces a number larger than light speed, and that particular sum was never the kind of quantity the speed limit was ever regulating in the first place. There's something genuinely elegant sitting in this resolution, and it deserves a moment before we move on. The impossible observation wasn't impossible at all. It was evidence that we had been quietly, understandably misapplying a rule about motion through space to a phenomenon that was never really about motion through space to begin with. The universe wasn't breaking its own laws. We were for a while simply asking the wrong version of the question. But naming the mechanism, space itself expands and that stretches light in transit, is not the same thing as explaining why space would do that, or what's physically driving it, or what determines exactly how fast it happens. For that, we need to go to the theory that first predicted an expanding universe against Einstein's own gut instincts, general relativity itself, and the specific equations that govern how the size of the universe actually changes across cosmic time. General relativity's central insight, published by Einstein in 1915, is that gravity is not a force reaching out across a fixed, unchanging space, the way Newton had described it 2 centuries earlier. Gravity is the curvature of space-time itself, caused directly by the presence of mass and energy. A planet doesn't orbit a star because some invisible rope is yanking it inward. It travels in the straightest possible line through space-time that has been bent, warped, curved by the star's mass. And that curved path is what we perceive from the outside as an orbit. Einstein's field equations relate the geometry of space-time directly to the matter and energy filling it. And crucially, in this picture, space-time is not a fixed, passive backdrop. It's a dynamical entity in its own right, capable of bending, warping, and, as it turns out, changing size over time, in direct response to what fills it. In the years right after general relativity was published, several physicists worked out solutions to Einstein's equations for a universe assumed to be homogeneous and isotropic, the same cosmological principle we already walked through, roughly uniform on the larger scales, with no special points and no special directions. Alexander Friedmann, working in the Soviet Union in 1922, found this solution first. Lemaitre found it independently in 1927. What are now called the Friedmann equations describe exactly how the overall scale of such a universe changes over time, governed entirely by how much matter, radiation, and other forms of energy happen to fill it. The central quantity in these equations is something called the scale factor, usually written as a running function of time. Think of it as a single number that tracks the overall size of the universe relative to some reference point. Not size in the sense of a boundary or an edge, but size in the sense of a ruler's length. If the scale factor doubles between two moments in cosmic history, then the distance between any two sufficiently far apart points that aren't gravitationally bound to each other, two galaxy clusters say, with no local gravity holding them close, has also on average doubled in that same span of time. The scale factor is the precise mathematical embodiment of the raisin loaf's dough expanding, or the balloon's rubber stretching, one single number describing exactly how much the fabric itself has grown. What the Friedmann equations reveal is that this scale factor's behaviour over time depends entirely on what the universe is actually made of, and in what proportions. A universe dominated by ordinary matter behaves one specific way. A universe dominated by radiation behaves a different way. And, this becomes critically important much later in the story, a universe with a significant component behaving like Einstein's old, abandoned cosmological constant behaves in a third way entirely. It doesn't merely expand, it accelerates. For most of the 20th century, that third possibility was treated as little more than a mathematical curiosity, a leftover option sitting in the equations that nobody had strong evidence to take seriously. Going into the final decades of the century, the two genuinely live hypotheses were both variations on the same basic theme: gravity eventually winning. Either the universe had enough total matter in it that gravitational attraction, acting across all of it, would gradually slow the expansion down over cosmic time, possibly even reversing it entirely into a future collapse sometimes nicknamed the Big Crunch. Or there was just barely not enough matter, and expansion would slow asymptotically toward a near standstill without ever fully reversing. Both of those live hypotheses shared one thing in common, and it's the exact assumption that made the discovery in the next chapter so genuinely shocking when it finally arrived. Everyone expected the expansion rate to be decelerating. Gravity pulls things together. More mass in the universe should mean more mutual gravitational attraction, should mean the expansion, whatever its ultimate long-term fate turned out to be, ought to be gradually steadily losing steam, the way a ball thrown straight up slows down as gravity pulls it back toward the ground. But before we get to that discovery, there's a piece of evidence that had to arrive first, because it's what transformed the universe used to be smaller and denser, from a mathematical implication of an expanding scale factor into something you could actually point an instrument at and detect directly with your own eyes. If space has genuinely been expanding for billions of years, then running that expansion backward implies the early universe was once compressed into an unimaginably hot, dense state. A hot, dense, early universe should have left behind a physical signature somewhere, still detectable today. And in 1965, almost entirely by accident, two engineers who weren't even looking for it found it. At Bell Labs in New Jersey, Arno Penzias and Robert Wilson were working with a large horn-shaped antenna, originally built for early satellite communication, which they'd repurposed for radio astronomy. Through 1964 and into 1965, they kept running into a persistent low-level background hiss contaminating their measurements. A faint hum of microwave noise that showed up no matter which direction in the sky they pointed the antenna, and that they could not, no matter what they tried, get rid of. So they did what any careful experimentalist does when faced with an unexplained instrumental problem. They went hunting for a mundane cause, methodically, one possibility at a time. They checked for stray interference bleeding in from nearby New York City. They checked for signals leaking over from ongoing military radar tests. They climbed up and found a pair of pigeons had built a nest directly inside the antenna's horn and had them relocated, cleaning out what Penzias would later describe with admirable scientific dryness as a white dielectric material. Pigeon droppings. On the off chance it was somehow responsible for the noise, none of it worked. The hiss remained stubbornly at exactly the same intensity from every direction, day and night, through every season, no matter what they removed or adjusted. Here's what made this discovery land at precisely the right possible moment in history. Unknown to Penzias and Wilson, a group of physicists at nearby Princeton University, Robert Dick, Jim Peebles, and their collaborators, were, at that exact same time, working through the theoretical prediction that an early, hot, dense universe should have left behind a faint uniform bath of leftover radiation, cooled by billions of years of subsequent cosmic expansion, down to a temperature only a few degrees above absolute zero, filling the entire sky equally in every direction all at once. They were in fact in the middle of building an instrument specifically designed to go hunting for exactly this signal. A single phone call between the two groups connected the observation to the theoretical prediction almost immediately. Penzias and Wilson hadn't found a stubborn equipment defect after all. They had detected the cosmic microwave background, relic light, from roughly 380,000 years after the hot, dense early universe had finally cooled enough for atoms to form and for light to travel freely through space for the very first time, rather than being instantly scattered by a dense, opaque fog of charged particles. That precise moment is often called recombination, and the light released at that instant has been travelling through an ever-expanding universe ever since, its wavelength stretched by that expansion from something originally resembling visible or infrared light, all the way down into the microwave range we detect on Earth today. This was not a subtle piece of evidence, it was a direct physical fingerprint of the universe's hot, dense infancy. A prediction generated purely from the mathematics of an expanding scale factor, run backward, and then confirmed independently by an entirely separate experiment that hadn't even set out to test it in the first place. It converted the universe's expanding and used to be smaller and denser from an elegant but abstract implication of a graph into a claim you could point an antenna at the sky and detect directly in every direction as a nearly perfectly uniform microwave glow. Penzias and Wilson would go on to win the Nobel Prize for a discovery that began, quite literally, with them trying to figure out why their antenna wouldn't stop hissing. Later, far more sensitive instruments, the COBE, WMAP, and Planck satellites, launched across the following 3 decades, mapped this cosmic microwave background in extraordinary, almost unsettling detail. What they found wasn't perfect uniformity after all, but tiny temperature fluctuations, differences of only a few parts in 100,000, scattered across the sky in a very specific statistical pattern. Those fluctuations are now understood as the faint fingerprint of the density variations that would go on, over billions of years, to seed the formation of every galaxy cluster, every filament of the vast cosmic web currently filling the night sky. In a very real sense, the cosmic microwave background is a baby photograph of the entire universe's future large-scale structure, encoded ahead of time in temperature differences smaller than 1/100th of a degree. Think about what that actually means for a moment, because it's easy to let the number slide past without registering it. every galaxy cluster, every supercluster, everything we'll eventually talk about later in this story regarding dark energy and accelerating expansion. All of it traces its origin back to microscopic density ripples, present in the universe when it was only 380,000 years old. So small that if you smoothed the entire observable universe's temperature out to a single value, these ripples would represent a deviation smaller than 1 part in 100,000 of that value. And yet gravity, working patiently over roughly 13.8 billion years, took those almost imperceptibly tiny differences and amplified them into everything. Every star, every planet, every galaxy, this planet, and eventually you watching this. With the cosmic microwave background in hand, cosmology stopped being purely observational astronomy, measuring where things are and how fast they're currently moving, and became something closer to precision physics, capable of extracting the actual composition of the entire universe. How much of it is ordinary matter? How much is unseen dark matter? And, as researchers refined the fit between theory and this data through the 1990s, how much of it appeared to be something else entirely? A component whose presence was mathematically required to make the numbers balance correctly, but whose physical nature nobody could yet explain. That something else turns out to be connected to the strangest, single, most surprising discovery this whole story has to offer. The discovery that finally broke the one assumption every cosmologist had been quietly carrying since Friedman first wrote his equations down. The assumption that gravity should, always and everywhere, be slowing the universe's expansion. By the 1990s, the central open question in cosmology had narrowed down to something that almost sounds like an accounting problem. Given how much matter the universe appears to contain, is there enough of it for gravity to eventually halt and reverse the expansion? Or not quite enough, leaving expansion to coast onward indefinitely, slowing but never fully stopping? 2 independent teams of astronomers set out to answer this directly, using a particular class of exploding star as a standard candle. The same fundamental logic Hubble had used with Cepheid variables decades earlier, but pushed out to vastly greater distances. Type 1. A supernovae occur when a white dwarf star, locked in a binary system with a companion, siphons matter off that companion until it crosses a very specific mass threshold and detonates in a runaway thermonuclear explosion. Because that threshold sits at nearly the same value across almost all such events, Type 1 supernovae explode with remarkably consistent peak brightness, making them exceptionally reliable distance markers, bright enough to be visible across billions of light years, and predictable enough that comparing their known intrinsic brightness to their observed apparent brightness gives a solid distance estimate, while their redshift, measured from the light of their host galaxy, gives an independent measure of just how much the universe has expanded since that light first departed. Put those 2 numbers together across a large sample of supernova, spread across a wide range of distances, and you can reconstruct the entire expansion history of the universe directly. Not just how fast it's expanding right now, but how that rate has changed across billions of years of cosmic time. Both teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High Z Supernova Search Team, which included Brian Schmidt and Adam Rees, went into the project expecting to measure some meaningful degree of deceleration. That was the entire point of the measurement: pin down exactly how much the expansion was slowing and use that number to figure out which of the 2 life scenarios, eventual collapse or indefinite, gradually slowing coasting, the universe was actually heading toward. What both teams found instead, published independently within months of each other in 1998, was that distant supernovae appeared noticeably dimmer than expected for their measured redshift, meaning they were, in effect, sitting farther away than a decelerating universe should have placed them. The only way to make sense of that pattern was if the universe's expansion had not been slowing down at all across cosmic history. It had been speeding up. Both teams spent a long time, years in fact, trying to rule out mundane, boring astrophysical explanations before either group was willing to publish something this radical. Could intervening cosmic dust be dimming the supernova in a way that just happened to mimic the signal? Could ancient supernovae simply be intrinsically different on average from nearby ones due to differences in the early universe's chemical makeup? Neither alternative held up against the full weight of the data set. The acceleration was real, and it was corroborated soon afterward by completely independent evidence buried inside the cosmic microwave background data from the previous chapter, which required exactly this kind of extra, unaccounted for energy component to make its own internal numbers balance correctly. This result earned Perlmutter, Schmidt and Rees the Nobel Prize in Physics in 2011, and it deserves to be understood as one of the single most genuinely surprising results in the entire history of observational cosmology, not because it confirmed a prediction everyone was hoping for, but because it overturned one that had gone essentially unquestioned for 7 straight decades. Gravity, acting on ordinary matter and radiation, should only ever be a decelerating force at the scale of the whole universe. There is no known way for ordinary gravity, sourced by ordinary matter, to make an expansion speed up on its own, which meant something else, something not yet accounted for anywhere in the equations, had to be responsible. Some component of the universe with a genuinely bizarre property. Instead of pulling things together at the largest scales, it appeared to be actively pushing space apart, and doing so more and more effectively as the universe grew larger and matter grew ever more diluted within it. Before we go further, it's worth pausing to ask a question a skeptical viewer should be asking by now, because a documentary that's been this insistent on intellectual honesty owes you a real answer to it. Redshift, distance ladders, an expanding fabric of space nobody can directly touch. Couldn't this whole picture simply be wrong? Isn't it possible astronomers are misreading the data and something far more mundane is actually going on? This isn't a fringe question. It's one professional cosmologist took seriously enough to spend real careers testing directly, and it's worth walking through exactly why the expanding universe picture survived that testing, rather than just asserting that it did. The most serious historical rival was something called the tired light hypothesis, proposed not long after Hubble's original discovery. The idea was elegant in its simplicity. What if light doesn't redshift because space is expanding, but because photons simply lose energy gradually as they travel across vast distances, scattering slightly off stray particles or losing energy through some unknown mechanism the farther they travel? Under this idea, the universe wouldn't need to be expanding at all. Distant light would just look redder because it had travelled farther, full stop. The way a long-distance phone signal used to get crackly and degraded the farther it had to travel down a wire. It's a genuinely reasonable-sounding alternative, and for a while it was taken seriously as a live competitor. Here's why it didn't survive contact with further evidence. If tired light were correct, and photons were simply losing energy through some scattering process during their journey, that scattering should also blur and smear the light out in the process. The way scattered light in fog gets diffuse and directionless. But distant galaxies, even extremely distant, heavily redshifted ones, remain crisp and sharp in our telescopes, with fine structural detail intact. Whatever is redshifting, that light isn't smearing it, which is exactly what you'd expect from cosmological expansion stretching a wavelength uniformly, and exactly what you would not expect from a scattering process. There's a second, arguably more decisive piece of evidence, and it comes from something called time dilation in distant supernova. If the universe is genuinely expanding, then not just wavelengths, but time itself, as observed from here, should appear to stretch out for very distant, fast-receding events. A supernova that actually brightens and fades over, say, 20 days as measured by someone standing right next to it, should appear, to us, to brighten and fade more slowly than 20 days, by an amount directly tied to its redshift, because the expansion is stretching out the arrival times of each successive photon in the light curve, not just their wavelengths. Astronomers have directly measured this effect in distant Type Ia supernovae, and it matches the predictions of an expanding universe with real precision. Tired light offers no mechanism at all for why the timing of a distant event should appear to slow down, only why its light might redden. An expanding universe predicts both effects from the same single underlying mechanism, and both effects show up exactly where predicted. Then there's the cosmic microwave background itself, sitting as a kind of final, independent tiebreaker. Tired light and every other serious alternative proposed over the decades would need a completely separate ad hoc explanation for why a nearly perfect, uniform thermal glow fills the entire sky at precisely the temperature and precisely the fluctuation pattern predicted by a hot, dense early universe cooling through genuine cosmic expansion. Nobody has produced a competing model that explains this observation as cleanly, using as few new assumptions as the expanding universe picture already does. This is really the underlying reason the scientific community moved from expanding universe as one hypothesis among several to something treated as extremely well established, not because any single measurement was unchallengeable on its own, but because multiple, completely independent lines of evidence, redshift distance relationships, supernova light curve time dilation, the existence and exact structure of the cosmic microwave background, the large-scale distribution of galaxies, all converged on the same picture, without any of them being designed to confirm each other. That kind of convergence from independent angles, using independent instruments built by independent research groups who in several cases weren't even trying to test the same question, is generally the strongest form of confidence science is capable of producing. It's not proof in the mathematical sense. Nothing in physics ever really is. But it's about as close as this field gets. Physicists needed a name for this component before they had anything resembling an explanation for it, and the name they settled on has become, over the following decades, one of the most publicly recognizable and privately frustrating terms in all of physics. Dark energy is the label attached to whatever is causing the universe's expansion to accelerate. It's worth being precise about what that label does and does not mean, because dark energy sounds to a casual ear like the name of a discovered thing, the same way electron or photon names a discovered thing. It isn't that. It's closer to a placeholder, a name for an effect whose underlying cause remains to this day genuinely unresolved. Current measurements, combining supernova data, the cosmic microwave background, and large-scale galaxy surveys, indicate that dark energy makes up roughly 68 to 70% of the total energy content of the universe, with the remainder split between dark matter at around 25 to 27% and ordinary matter, the stuff of stars, planets, and everything directly detectable through electromagnetic radiation, at only around 5%. Sit with that ratio for a second. On the scale of the entire cosmos, the component we can directly observe, touch, and build instruments out of accounts for a sliver of what's actually out there. The dominant component is the one driving the accelerating expansion, and it's also frustratingly the one we understand the least. The leading simplest explanation is to treat dark energy as equivalent to Einstein's old cosmological constant, not, this time, inserted artificially to hold the universe static, but reinterpreted as a genuine constant energy density inherent to empty space itself, sometimes called vacuum energy. In this picture, as the universe expands and its total volume increases, the total amount of matter inside it stays fixed, meaning its density thins out. The same amount of matter spread across an ever larger volume, growing sparser over time. But if empty space itself carries a fixed energy density, then more space simply means more total vacuum energy, scaling directly with the growing volume. Early in cosmic history, when the universe was small and matter was densely packed, matter's gravitational pull dominated completely, and expansion was indeed decelerating, exactly as everyone originally expected. But as the universe kept expanding and matter kept diluting, the fixed density vacuum energy eventually overtook matter's gravitational influence. And once it did, its repulsive effect began to dominate, and the expansion started accelerating instead, somewhere around 5 to 6 billion years ago, based on current estimates from the combined supernova and cosmic microwave background data. This is an elegant story, and it fits the observational data astonishingly well enough that it now forms the backbone of the standard model of cosmology, commonly abbreviated lambda-CDM, where lambda is the symbol for the cosmological constant, and CDM stands for cold dark matter. But elegance in fitting data is not the same thing as actually understanding the underlying physics, and this is exactly where dark energy's honest weak point sits. Quantum field theory, the framework describing how particle physics works at the smallest scales, independently predicts that empty space should carry a non-zero vacuum energy, arising from quantum fluctuations that are, in principle, present everywhere, even inside a total vacuum with no particles in it at all. This should, in theory, let physicists calculate a predicted value for vacuum energy density from first principles, and simply compare that prediction against what cosmological observations actually require. When that calculation is actually attempted, the result is one of the most notorious mismatches in the entire history of physics. Depending on exactly how the calculation is framed, quantum field theory's naive prediction for vacuum energy density comes out somewhere between 60 and 120 orders of magnitude larger than the value cosmological observations actually require to explain the accelerating expansion we measure. That is not a modest discrepancy needing a small correction factor. It is, by an enormous margin, the largest disagreement ever recorded between a theoretical prediction and observed physical reality, often described without much exaggeration as the single worst prediction physics has ever produced. Let that number sit for a second, because it's genuinely hard to build intuition for it. If quantum field theory's naive calculation were merely off by a factor of 1,000, that would already be an embarrassing gap. A factor of 1,000,000 would be a full-blown crisis. This is off by somewhere between a 1 followed by 60 zeros and a 1 followed by 120 zeros. There isn't a good everyday comparison for a mismatch that size, because nothing in ordinary experience is ever wrong by that much, and still gets taken seriously as a scientific framework. Quantum field theory works magnificently everywhere else it's ever been tested. This is the one place it breaks catastrophically, and nobody currently knows exactly why. This mismatch is usually called the cosmological constant problem, or more evocatively the vacuum catastrophe, and it remains, as of the most recent research, genuinely unresolved. Various approaches attempt to explain why the naive calculation overshoots by so staggeringly much, some invoking as yet undiscovered symmetries in nature that should cancel most of the vacuum energy down to nearly, but not quite, zero. Others proposing that dark energy isn't a true unchanging constant at all, but a dynamical field, sometimes called quintessence, whose energy density can shift slowly across cosmic time rather than staying perfectly fixed forever. None of these approaches currently commands the kind of overwhelming evidence needed to settle the question. What's known, established firmly across multiple independent lines of evidence, is that the universe's expansion is accelerating, and that something with the large-scale behaviour of a repulsive space-filling energy is responsible. What remains genuinely unknown, despite decades of dedicated effort from some of the most capable physicists alive, is what that something actually is, at a fundamental level. It's worth pausing here, honestly, because this is exactly the kind of open uncertainty this documentary promised right at the start, to sit with rather than paper over. We are not withholding an answer for dramatic effect. There genuinely isn't a settled one yet. The acceleration is measured repeatedly, precisely, from multiple independent angles. The cause is not identified. That gap between a confirmed effect and an unconfirmed cause is one of the largest open problems remaining anywhere in physics, and it sits quietly underneath every single galaxy you can see rushing away from every other one. And as if that weren't already enough uncertainty for a single field of science to be carrying, an entirely separate problem emerged over the following decades. Not about what dark energy actually is, but about something that sounds, on its face, like it should be far simpler to pin down. Exactly how fast the universe is expanding right now, today. The Hubble constant, the proportionality figure connecting a galaxy's distance to its recession speed, first estimated by Hubble himself back in 1929, should, in principle, be a single, fixed number describing the universe's current expansion rate. Measure it carefully enough, using enough independent methods, and those methods ought to converge on the same value, within their respective margins of error. That convergence is generally exactly what happens when different measurement techniques are correctly probing the same underlying physical quantity. For the Hubble constant, that convergence has not happened, and the persistent growing discrepancy between two broad families of measurement is now widely referred to across the field as the Hubble tension. The first family of methods measures the expansion rate using what's sometimes called the local or late universe approach, building what's known as a distance ladder using nearby extremely well calibrated standard candles. Cepheid variables, the same class of Star-Leavitt and Hubble used a century ago, calibrated today using extremely precise parallax measurements from missions like Gaia, then extended outward using Type 1a supernovae in more distant galaxies, calibrated in turn against the Cepheids visible in closer ones. This ladder-based approach, refined over decades and pushed to very high precision by projects like the SH0ES collaboration, led by Adam Rees, consistently produces a Hubble constant value in the range of roughly 73 kilometers per second per megaparsec, meaning for every additional megaparsec of distance, about 3.26 million light-years, a galaxy's recession speed increases by roughly 73 kilometers per second. The second family of methods measures the expansion rate using an entirely different approach, taking the extraordinarily detailed structure of the cosmic microwave background from a few chapters back and fitting it against the full lambda CDM cosmological model to extract, among many other cosmological parameters, an inferred value for today's expansion rate, essentially predicting what the Hubble constant should be right now based on the physics of the very early universe evolved forward mathematically across nearly 14 billion years. This approach, using the extraordinarily precise cosmic microwave background data from the Planck satellite, consistently produces a noticeably lower value, around 67 kilometers per second per megaparsec. That difference, 73 versus 67, roughly a 9% discrepancy, might sound modest at first glance. But both measurement methods have become precise enough that their respective margins of error no longer comfortably overlap. This is not, at this point, something you can easily wave away as ordinary measurement noise. Each method, evaluated entirely on its own terms, appears to be measuring its target value quite accurately, and yet they disagree with each other consistently across repeated independent refinements of both approaches over more than a decade of dedicated effort. There are, broadly, 3 categories of explanation currently being pursued, and it's worth stating them with the same appropriate uncertainty the researchers working on this would themselves use. One possibility: there remains an unidentified systematic error somewhere in one or both of the measurement chains, some subtle calibration issue buried in the distance ladder, or some unexamined assumption baked into the cosmic microwave background model fit. That, once found and corrected, would bring the two values back into agreement. This remains a genuinely live possibility, and it's the outcome many cosmologists would, in some sense, quietly prefer, because it wouldn't require rewriting any fundamental physics, just refining measurement technique. But despite years of dedicated scrutiny from multiple independent research groups specifically hunting for such an error, none sufficient to fully resolve the discrepancy has been conclusively identified. A second possibility: the discrepancy is genuinely telling us something new about the universe's underlying physics, that the standard lambda-CDM model, while extremely successful at fitting an enormous range of other observations, is subtly incomplete in a way that specifically affects how the early universe, cosmic microwave background inferred expansion rate, should be projected forward to the present day. Various proposed modifications, additional exotic particle species present in the early universe, dark energy that behaves slightly differently than a pure constant, small alterations to how dark matter interacts, have all been explored as ways to close this specific gap. But as of the most recent analyses, no single proposed modification has been broadly accepted as the clear resolution, and several of the proposed fixes actually create new tensions with other independent data sets even as they ease this particular one. A third possibility, less commonly emphasized but taken seriously by some researchers, is that both measurements might simply be correct, and the discrepancy reflects some kind of genuine underlying complexity in how expansion is measured across different cosmic epochs or environments, that the Hubble constant may not be quite as universally simple and single-valued a quantity as the standard model currently assumes it to be. What can honestly be said, without overstating the case in either direction, is this: the Hubble tension remains unresolved. It is not a fringe anomaly quietly waiting to be tidied up in some future footnote. It has become one of the most actively debated open problems in observational cosmology today, discussed at length in the field's major conferences and journals, and it may, depending on which of the explanations above eventually proves correct, turn out to be either a solvable measurement puzzle or a genuine crack running through our best current model of how the universe actually works. It's a fitting complication for this story to run into, because it means even the single most basic sounding number in this entire mystery, how fast is the universe expanding right now, today, does not currently have one single universally agreed upon answer. We know the universe is expanding. We know that expansion is accelerating. We do not know, to full precision, exactly how fast it's happening at this precise moment, because our two best methods of finding out disagree with each other in a way nobody has yet fully explained. There's a more recent complication worth pausing on here, because it's a good example of how this entire field never really settles into comfortable certainty for very long. When the James Webb Space Telescope came online and began peering deeper into the early universe than any previous instrument had managed, it started finding something unexpected sitting out near the very edge of what's observable at all. Galaxies that appear to have formed and grown surprisingly large and mature far earlier after the Big Bang than the standard model of galaxy formation had predicted was possible. This isn't, to be clear, a challenge to the expansion of the universe itself. The redshift measurements underlying it are the same well-tested technique this entire story has been built on. It's a challenge to a related but separate question. How quickly matter, in the aftermath of that hot, dense early state, was actually capable of clumping together into fully formed galaxies. Some of these early distant galaxies appear brighter, more massive and more chemically developed than existing models of star formation comfortably allow for the amount of cosmic time that had actually elapsed by that point. Researchers are still actively working through what this means. It could point to gaps in our understanding of how quickly the first stars and galaxies were able to form and grow, rather than anything to do with the expansion story itself. It could point to subtler issues with how brightness and mass are being estimated at such extreme distances. It's mentioned here not because it overturns anything we've walked through so far, but because it's an honest current example of the field still actively surprising itself. A reminder that even with a century of confirmed physics behind it, cosmology is still very much a live working field, not a closed book with a final chapter already written. Set the unresolved tension aside for a moment, because whichever precise value eventually wins that argument, the broader picture, an accelerating expansion driven by dark energy, layered on top of the ordinary expansion Hubble first measured a century ago, carries implications worth sitting with carefully. They extend well past this century's open questions and straight into the deep future of absolutely everything. If dark energy behaves across cosmic timescales roughly the way the simplest cosmological constant model predicts, a fixed energy density inherent to space itself, growing in total effect as space itself grows larger, then the acceleration we've measured over the past several billion years is not a temporary phase the universe is passing through. It should continue indefinitely, and its effects compound over time in a genuinely strange way. Here is the specific consequence worth understanding clearly, because it's easy to describe and much harder to actually absorb. As accelerating expansion continues, the space between us and increasingly distant galaxies will keep stretching at an ever-increasing rate. There exists, as a direct mathematical consequence of this ongoing acceleration, something cosmologists call the cosmic event horizon, a boundary currently estimated at roughly 16 billion light-years away, beyond which the space between us and any object is right now growing so fast that light emitted from that object today will never be able to cross the intervening, ever more rapidly expanding gap to reach us, no matter how much time passes in the future. It's not that the object is receding faster than light in the sense forbidden by relativity. We already walked through why that particular fear doesn't apply. It's that the accumulated growth of space between here and there is outrunning light's ability to close that growing distance permanently, with no way for it to ever catch up. This means, and it's worth letting the actual consequence fully register, that as time goes on, an ever-increasing number of galaxies currently visible to us will cross beyond this horizon. Not by physically moving anywhere, simply because the space between us and them will grow too fast for their light to keep making the crossing. Their light already in transit toward us will continue arriving for a very long time yet, growing steadily dimmer and more red-shifted with every passing eon. But eventually, over cosmic timescales measured in the tens of billions of years, even that trickle will fade to nothing. Those galaxies will become permanently, physically unreachable and unobservable, cut off from us by nothing except the accumulated quiet growth of space itself. Run this forward far enough, trillions of years, well beyond the current age of the universe, which is itself only about 13.8 billion years old, and the implication for any future civilization, or any future version of astronomy, becomes genuinely unsettling in its quiet, almost mundane way. Local, gravitationally bound structures, our own local group of galaxies, likely to eventually merge together under their own mutual gravity into a single larger galaxy, would remain intact, because gravity, locally, overwhelms the accelerating expansion at those close distances. But beyond that local, bound neighbourhood, an observer far enough in the future would find the sky increasingly, then eventually almost entirely empty. All the other galaxy clusters, all the other structures currently visible across the entire observable universe, would have receded beyond the cosmic event horizon, their light forever unable to arrive. This is sometimes framed, evocatively but not inaccurately, as a kind of eventual cosmic isolation, not annihilation, not collapse, but a slow, physically enforced solitude, imposed not by any object actively moving away, but by the space between objects simply outgrowing light's ability to bridge it. Some cosmologists have noted, with a mixture of scientific detachment and genuine unease, that a sufficiently distant future civilization, evolving inside such an isolated local galactic remnant, might have no direct observational way of ever discovering that a wider, expanding universe, or even a Big Bang, had ever existed at all. The evidence would by then be permanently outside the reach of any telescope they could ever build, no matter how advanced. It's a strange thought to sit with. Our own moment in cosmic history is a genuinely privileged one, observationally, not because we're special in any cosmic sense, but simply because we happen to be early enough that the wider universe is still visible to us at all, right now, tonight, if you go outside and look up. That projection assumes dark energy stays exactly what the simplest model says it is, a true, fixed, unchanging constant. It's worth being honest that this is an assumption, not a certainty, and that a handful of competing, still viable models paint a meaningfully different picture of how this all ends. If dark energy is instead a dynamical field, something whose strength can genuinely shift across cosmic time, rather than staying perfectly constant, a few different long-term futures open up, and none of them can currently be ruled out with the data we have. In one version, sometimes called the Big Rip, dark energy doesn't just stay constant, it strengthens over time, and its repulsive effect eventually grows powerful enough to overcome not just the gravity-binding galaxy clusters together, but the gravity holding individual galaxies together, then solar systems, then eventually the electromagnetic forces holding planets, and finally atoms themselves, together. In this scenario, expansion doesn't quietly isolate everything from everything else over trillions of years. It tears the fabric of every bound structure apart directly, in a finite, calculable amount of time, ending not in slow cosmic loneliness, but in a much more abrupt unravelling of matter itself. Current data doesn't favour this outcome, but it hasn't been ruled out either. In another version, dark energy could weaken over time rather than strengthen, easing the acceleration we currently measure, potentially even reversing it far enough in the future that gravity reasserts itself as the dominant force again, sending an already vast, already diffuse universe into a slow contraction, back towards some kind of eventual collapse, an echo of the Big Crunch scenario that seemed like a live possibility before the 1998 supernova discovery ruled it out under the old simpler assumptions. Under this newer dynamical dark energy framing, it isn't fully ruled out again. It's just now a much less favoured, much longer odds possibility than it once was. And there's a version, favoured by a fair number of researchers as the most likely outcome given current evidence, sometimes called heat death, where the simplest cosmological constant picture from a few chapters ago simply continues indefinitely. Matter thins out, stars burn through their fuel and go dark one by one over trillions of years, black holes slowly evaporate over timescales that make even trillions of years sound brief, and the universe settles into an almost perfectly uniform, cold, extremely low energy state. Not destroyed, not torn apart, just gradually, thoroughly emptied of anything capable of doing work or supporting complexity of any kind, expanding forever into an ever thinner, ever colder version of itself. We are extrapolating a genuine, well-measured trend an enormous distance beyond anything we've actually directly observed, using a model whose underlying physical cause we still, honestly, do not fully understand. The deep future described across these last two chapters is a serious mainstream scientific projection built on our best current model. It is not a certainty, and any documentary that presented it as one would be doing you a disservice. What is not in serious doubt, regardless of which specific ending eventually turns out to be correct, is the underlying mechanism responsible for all of them, an accelerating expansion of space itself, gradually separating everything not locally bound together by gravity at a rate that is not slowing down, and that our best current physics does not yet fully know how to explain. We've now leaned on the phrase measuring cosmic distance for most of this documentary, so it's worth stopping once to actually walk through how astronomers pull off something that sounds almost impossible, figuring out how far away an object is without ever being able to travel to it, touch it, or bounce a signal off it and time the return. For the nearest stars, the technique is refreshingly close to something you already know intuitively. Hold a finger up in front of your face, close one eye then the other, and watch your finger appear to jump slightly against the background behind it. That apparent shift is called parallax, and the closer the object is to your eyes, the bigger the jump. Astronomers do the exact same thing on a cosmic scale, using the widest baseline available to them, Earth's own orbit around the Sun. Photograph a nearby star in January, then photograph it again in July, 6 months later, when Earth has moved to the opposite side of its orbit, a genuine baseline of about 186 million miles, and that star will appear to have shifted very slightly against the much more distant background stars behind it. Measure that tiny angular shift precisely enough, and simple geometry, the same geometry you'd use to figure out how far away your finger was from the size of its jump, hands you the star's actual distance. This works beautifully for relatively nearby stars, but the angles involved shrink fast with distance, and even the most precise modern instruments, like the European Space Agency's Gaia satellite, purpose-built for exactly this measurement, eventually run out of precision at a few tens of thousands of light years. That's a respectable chunk of our own galaxy, but it's nowhere close to reaching another galaxy entirely, let alone the galaxies billions of light years away that this whole story has been built around. That's exactly the gap Henrietta Swan-Leavitt's Cepheid variables filled back in Chapter 4. Once parallax has calibrated the true intrinsic brightness of nearby Cepheids with real precision, that same brightness to pulse period relationship can be applied to Cepheids much farther away, wherever they can be individually picked out and timed, inside other relatively nearby galaxies. Compare a distant Cepheid's known true brightness to how dim it actually appears from Earth, and you get its distance, using the same basic light fades predictably with distance logic, extended far beyond parallax's reach. This is the first rung of what astronomers call the cosmic distance ladder, and it's a genuinely apt name. Each technique's results calibrate and extend the reach of the next one, rung by rung, out to progressively greater distances, with each rung's accuracy ultimately depending on how well the rung below it was measured. Cepheids themselves eventually become too dim to individually resolve, even in the most distant galaxies where they can still be picked out at all, which is exactly the gap Type 1a supernova fill next. The same exploding white dwarfs from the deceleration that wasn't Chapter. Because supernovae are catastrophically briefly brighter than any single star, they remain visible across distances Cepheids could never reach, billions of light years rather than tens of millions. And because their peak brightness is so consistent across nearly every such explosion, calibrating them against Cepheids in the more nearby galaxies, where both techniques can be used side by side, lets astronomers extend the ladder's reach dramatically further outward, all the way to the distances involved in measuring the accelerating expansion itself. There's one more rung worth knowing about, because it offers a genuinely independent cross-check on everything above it, using a completely different physical mechanism. In the early universe, before atoms had even formed, ordinary matter and light were locked together in a hot, dense plasma, and sound waves, genuine pressure waves, physically identical in kind to the ones carrying your voice through the air right now, rippled through that plasma, expanding outward from countless tiny density fluctuations. When the universe cooled enough for atoms to form, at the same moment that released the cosmic microwave background, those sound waves froze in place, leaving behind a very specific, calculable preferred separation distance between regions of slightly higher matter density, baked permanently into the large-scale distribution of galaxies that would eventually form from that matter. Astronomers call this signature baryon acoustic oscillation, and because the physics predicting its exact size is extremely well understood from first principles, it functions as its own kind of cosmic ruler, one that doesn't depend on Cepheids or supernovae or anything from the distance ladder at all. And it independently confirms the same expansion history the ladder produces. This matters for the same reason the tired light discussion mattered a few chapters back. It's not one fragile chain of measurement holding up this entire story. It's several genuinely independent methods built on entirely different physics, converging on compatible answers. Parallax doesn't know Cepheids exist, baryon and acoustic oscillations don't care about supernovae, and yet lay their results side by side across the full range of distances this documentary has covered, and they agree, which is ultimately the quiet, unglamorous reason any of the far stranger claims in the rest of this story are worth taking seriously at all. Before returning to where this story began, it's worth gathering, honestly and without any embellishment, exactly what remains unresolved. Because a documentary that has spent this long insisting on scientific honesty owes its final act the same discipline it demanded of every chapter before this one. We know, with very high confidence, backed by multiple independent lines of evidence that don't depend on each other, that the universe is expanding, that this expansion is well described by the Friedmann equations derived from general relativity, and that it is currently accelerating rather than decelerating. We do not know, at a fundamental physical level, what dark energy actually is. The cosmological constant interpretation fits the observational data remarkably well, but the enormous mismatch between that observed value and the value predicted by quantum field theory, the vacuum catastrophe from a few chapters back, remains completely unresolved, and it is not a minor loose thread hanging off an otherwise finished picture. It sits at the centre of one of the largest known gaps between two of physics' most successful frameworks: general relativity, which describes gravity and the large-scale universe magnificently, and quantum field theory, which describes particles and forces at the smallest scales magnificently, and which currently cannot be made to agree with general relativity's own cosmological requirements without an error stretching across dozens of orders of magnitude. We do not currently have a single, agreed-upon value for the Hubble constant, the precise rate of expansion right now, today, because of the unresolved tension between early universe and late universe measurement methods, a discrepancy that has persisted, and if anything sharpened, as measurement precision has steadily improved over the past decade, rather than quietly resolving itself the way most such disagreements eventually do. We do not know, with certainty, whether the universe is spatially infinite, or an extremely large finite volume that simply appears flat within the small portion of it we're capable of measuring. Current data constrains the geometry to be very close to flat, but very close to flat and exactly infinitely flat are not observationally distinguishable with current instruments, and may never be if the true finite size, should one exist at all, turns out to be sufficiently larger than the volume we're capable of ever directly observing. And we do not know, in any way, current physics can currently test what, if anything, the concept of outside the universe would even mean. This is worth being genuinely precise about, because it's the exact question this whole documentary has been circling since its opening seconds, and it deserves an honest, careful answer, rather than either false certainty in one direction or evasive mystery mongering in the other. The balloon analogy from a few chapters back offered one useful, careful way to think about this. The balloon's two-dimensional surface is the entire universe available to creatures living directly on it, and the three-dimensional space the balloon expands into is not part of that universe at all. It's not a place those creatures could ever travel to, because into isn't even a meaningful direction from inside a two-dimensional surface. If our own three-dimensional universe is, in some genuine sense, analogous, the surface of some larger structure, then whatever it's expanding into, if that phrase even applies here at all, would not be a place located anywhere within our own three spatial dimensions. It would not be reachable by any spacecraft, detectable by any telescope, or describable using any of the physics built specifically to describe things that exist inside our universe. Because that physics was built entirely from observations made, from inside it, and only ever tested against things inside it. But it's important to be honest about exactly what this establishes and what it doesn't. This is not a confirmed finding. It's at best a mathematically coherent possibility, illustrated by borrowing an analogy from a lower dimensional case we can visualize precisely because we happen to exist outside it, looking in. Whether our actual three-dimensional universe is genuinely analogous to that balloon's surface, embedded inside some higher dimensional structure it's expanding into, or whether it's instead something for which the very question expanding into what is simply a category error, built from words that don't actually combine into a meaningful claim, the way asking what is north of the North Pole fails to describe a real, findable direction rather than merely a hard-to-locate one. That is genuinely, as of current physics, an open question. Some theoretical frameworks, particularly certain approaches to quantum gravity and string theory, do explore mathematically consistent pictures of higher dimensional spaces our universe might be embedded within. Some even speculate about an eternally inflating higher-level structure occasionally budding off separate expanding bubbles, our own universe potentially being just one such bubble among an unknown, perhaps unknowable number of others. None of these ideas currently have any direct observational confirmation, and it's worth being unusually blunt about that, given how often this specific idea gets treated casually elsewhere online, as though it were an established fact rather than a speculative mathematical extension. They remain genuinely speculative frameworks, built to explore what's mathematically possible within our current understanding of physics, not established descriptions of what is actually physically real. The honest answer, the one this documentary owes you rather than a more satisfying but less truthful one, is this. Physics can tell you, with real confidence, how the universe is expanding, and it can tell you, with somewhat less confidence but still substantial supporting evidence, why dark energy, whatever its ultimate underlying nature eventually turns out to be. But whether the very question, what is it expanding into, describes something real that we simply haven't measured yet, or whether it's a question built from an intuition, space as a container, expansion as something that must necessarily happen inside some larger space, that may simply not apply to space itself at the deepest level, is not something current science can answer yet. It may, in fact, be a question that requires an entirely different kind of physics than anything we currently possess, even to properly ask it in the first place. Go back for a moment to the very beginning of this, a clear night sky, apparently motionless, apparently eternal, the same stars sitting in the same places a person standing under them 1,000 years ago would have recognized instantly, without a moment's hesitation. That stillness was never real. It was always a limitation of the instrument doing the looking. A human eye, evolved across a few 100,000 years, calibrated to notice motion across seconds and minutes, entirely blind to a kind of motion that only reveals itself across the careful, patient accumulation of decades of measurement, spread across thousands of distant points of light, compared painstakingly against one another by people who mostly didn't live to see how their individual piece fit into the final picture. We open this whole story with 3 anomalies stacked on top of each other, everything receding from us specifically, as though we sat at some impossible centre, that recession growing faster with distance, in a relationship far too clean to ignore, and past a certain distance, that recession appearing to exceed the speed of light entirely, breaking a rule that had never been broken anywhere else. Each of those anomalies, taken individually, looked like it might demand an exotic answer, maybe even an impossible one. Taken together, patiently unpacked across a full century of observation, they resolved into something both stranger and, in its own quiet way, more elegant than any single exotic answer could ever have been. There is no centre, because this was never an explosion into pre-existing space, the way our intuition would have it. There is no violation of relativity's speed limit, because it was never galaxies racing through space at all. It was the space between us and them, quietly, continuously growing, everywhere, all at once. A process relativity's speed limit was simply never built to restrict in the first place. And so we arrive back at the exact question this whole film is named for, and it's worth stating plainly, now that every piece is finally in place, why that question was subtly malformed from the very moment we first asked it.